For the past 20 years, when you think about it, we have been talking about qualitative experience, user experience, without really knowing and really trying to deeply understand what this was about. With this new experiment at Cisco, we've been studying cognitive networks, which is a new type of networking technologies that will allow to learn what QE is about. I'm JP Vassar, Cisco Fellow, VP of Engineering and Driving AI/ML for Cisco Networking. I'll be covering today this topic of cognitive networks, whereby we can use machine learning AI to model what QE is about so that we can drive a network to optimize QE as opposed to being too network-centric, which is basically what we've been doing for so many years now. Okay, so what is cognition about? I won't go through the formal definition in neuroscience, but it's basically about the mental action or process of acquiring knowledge and understanding through thought, experience, and the senses. What do we mean by that? As you will see, instead of guessing what would drive the experience of a user, we'll be using machine learning to learn what drives QE. So let's have a look at this short video, and that's going to ring a bell, I'm sure. How many times have you seen people complaining about the network reach out to the application team and say, there is an issue in terms of qualitative experience, and then as a follow-up, the application team would reach out to the networking team and say, that must be because of a network. Then in turn, what the networking team would do is to investigate, try to find some reasons why there might be an issue in terms of QE using a plethora of tools such as press route, a different kind of probing mechanism with advanced measuring such as thousand eyes, and trying to basically prove that it is not because of a network, or in some cases find out the root cause of it. So we wanted really to find out another way to really understand what drives the QE, what makes the user happy or unhappy about the experience. If you look back at the past 20 years, we have had a plethora of technologies so that we can measure the delay, the packet loss, and so on and so forth. We have been using many metrics at multiple layers, even at the transport layer with ART, application response time, for example, technologies to really understand different kind of phenomenon within the network. Recently, we have published a white paper, by the way, about MIF, microfailures. You will find the reference below the video when we try to understand microphenomenon that may have an impact on QE. What has been proposed at the IETF was to look at different classes of application, and for each of them, look at the sensitivity and basically are very sensitive to loss, packet, and jitter. Try to assign a weight, if you will, so that we can assign, basically we can compute a formula that would reflect the health of a given application. But in this case, and there are many, many examples like that, whether it's coming from Cisco or other solutions, where you try to come up with this kind of simplification of a QE, you would assign a score, you would assign some weight, you would be using this network-centric variable and basically come up with a score between 1 and 5 or 1 and 10, as we did for the MOS score in the case of voice many years ago. So what we wanted to do in this case was to have a very different approach. The way it has been done today, as I said, is really to look at this kind of variable and compute this kind of magic formula that may be revisited from time to time so that you can change a little bit the weight, you can modify the way you measure the variables. The idea of cognitive networks was to say, can we really find some kind of ground truth that would be coming from a user, then take some cross-layer telemetry, and then start using a machine learning model to really infer and predict the QE for which we've got enough labels, so ground truth, because it would be coming from a user, and trying to correlate that with all of these parameters and really understand what QE is being driven by. And this is really the core of cognitive networks. And obviously, if you start to have a model that predicts for you what will be the QE, you can start to inspect the model, and thanks to interpretability toolset, you can start to understand what drives the QE. As of today, there's almost no way to do that. The way you would be doing this is basically by using this magic formula. You would try to understand, using some subject matter expertise, what might be driving these kind of issues. And then based on that, you would try to trigger some action to solve the issue in the first place. Well, with cognitive networks, what we believe is that if you have a model that can compute, infer, predict, whatever term you prefer to use, the QE using the cross-layer telemetry, then if you can root cause by doing some model inspection, then you may be able to trigger some actions in the network so that you can start tuning the network automatically. But now, instead of trying to optimize some network-centric KPIs, you may want to optimize the QE in the first place, which would be a radical shift compared to what has been done before. So let me show you the components of such a brand new approach. First, you need to have some telemetry. I'm stating the obvious. It could be networking-driven telemetry, going from high-frequency probing kind of mechanism, coming from, in the case of Cisco, DNA, Viptela, Meraki, and ThousandEyes. And then you may want to look at application-level feedback and labels. We've been collaborating with Microsoft for years. We have done some experiments. We even have shipped some products whereby we get feedback directly from the application with a few minutes of intervals. And we have some categorical feedback that tells us what is the experience as seen by the application itself. I absolutely believe that such a layer 7 signaling mechanism could add a lot of value to networking in the future, as discussed in the white paper I was mentioning before. But of course, if you want to train a model, you do need to have some ground truth and feedback provided by customers. And this is what we did. We managed to have a large-scale experiment at Cisco thanks to the 6,000 or so employees who agreed to give us some live and real-time feedback on the quality of voice and video that we could couple with extremely rich telemetry coming from WebEx across all of the layers. And this kind of labels is, of course, absolutely critical to the process of modeling. And then you may want to use also some proxy signals, which is something we've done as well. Now, thanks to the telemetry across all of the layers, coupled with explicit user feedback, and in our case, we didn't come up with a number between 1 and 5, but something very simple, such as, I have a good experience, I have a bad experience, because this is usually what reflects the better, if you will, what the user experience is about. Then we have trained multiple machine learning models. It was the result of very deep analysis, very deep and fundamental work on the technology side. And then we have verified that indeed we could model the QE from a user. The last piece of this architecture, as I said before, is to give the token, if you will, to some other algorithm that may be able to play with different kind of remediation actions, along with the prediction of a QE model about the QE of a user. And then it would be able to play with multiple tools, if you will, so that you could improve your network in terms of QE as opposed to trying to reduce the delay, the average load of the links, and so on and so forth, which again is a very big paradigm shift towards full self-healing networks. I won't have a time in a video of about 20 minutes to go through the logic behind the bot that has been used to collect this data. But as you can imagine, you need to be a little bit careful. You don't want to send too many requests to your users. In our case, we wanted to limit it to 1 or 2 feedback every day. you want to have the maximum information when you request such a feedback, which is of course pretty expensive to get. You don't want to bother the users too much. So what we did was to have a different algorithm that was using some kind of active learning when we would try to understand who are the users we want to send the request to so that the feedback has a maximum value for the model, and in consequence, as a consequence, we can improve the quality of the model. So we've been looking at many cycles to do that. And again, I'm skipping the details, but you can find more information in the white paper if you are interested. We came up with multiple probing strategies in order to, with many mechanisms to suppress some feedback in some cases. We also came up with strategies so that we can understand when there were some biases, because sometimes, it's all about subjectivity. You may request feedback, you may get some labels for which you don't believe that the user has correctly understood what was asked. We gave also a lot of examples of the strategies we put together so that we could have the most valuable data set of users' feedback. We've had, it was really fun to do that. Here, I'm just showing you some plots with basically the number of users that participated to the survey, the level of positivity, what was the percentage of time we had a thumbs up, thumbs down kind of feedback. Have we seen some users that tend to be too optimistic, too pessimistic, that would start to not provide some good feedback, would provide feedback but too late, so they may not be related to their current experience, and so on and so forth. Again, we're detailing all of that, that kind of feedback in the white paper. What was very, very interesting now was if you look at the telemetry, and of course it's a very rich set of telemetry. We've got the WebEx telemetry across all layers. You've got the bot, which has been pruned, and we have removed some noise, of course, in the labels provided. We used layer 7 kind of feedback as well. You could use also, Thousand Eyes telemetry, which is very rich, as I mentioned before, some MIF telemetry. We took all that kind of telemetry, and we started to do multiple trainings using different kind of features, and even, I would say, multiple kind of algorithms. So the one that I'm showing you to now is an ensemble of gradient boosted trees that are known as being extremely efficient when you play with tabular data. That's the one we have used. Again, we used multiple GBT trees, not just one. And we came up with different strategies to combine the outcome. And what you can see on that video is that over time, you could see that the trees are trained and to basically start choosing the most important features. At the same time, you can have a look at the efficacy of the model. You see the log loss in this case going down pretty nicely, as you can see on the top right. And we looked also at some data projection between the prediction and the bot labels. And you can see that over time, we're really learning a lot of information from these labels, which was extremely encouraging. At the end of this experiment, we had, this is not actually the latest screenshot, we had more than 100,000 labels that were used in order to train the set of algorithms. These labels, for each of them, remember, we had dozens, if not hundreds, of variables across the layers that could be used to efficiently train the model. So in this case, what I'm showing you, I just took a 50 feature space, reduced to less dimension. This is actually 3D in this case. This is a representation of 13,000 WebEx reports. And you can see for each of them, remember, a report is made of dozens of dimensions. You see the green, and which are good, and the bad, which are red. And you can see the true labels as opposed to the predicted labels. You do see that over time, we have very good learning of this kind of pattern that has been captured by gradient boosted trees. But of course, we wanted to look over time. Is it just a matter of taking a report with multiple dimensions over 1 minute, or should we have a look at sequence models, which is what we did? Would the QE and the perception of the user be driven by the last 1 minute, or might it be spread across a longer period of time? And this is, of course, what we found out, which is that you need to look at the sequence of models, because in some cases, you may have some subtle issues and they start to accumulate and contribute to the QE of a user, as opposed to being just what happened in the past 1 minute. And this is something we saw years ago in voice and video. You could see that if you keep having a fairly high number of glitches, if you will, the perception may be worse than having a severe issue, but for a short period of time. So this is exactly what we've seen. And this is really where you do see the power of using machine learning to capture this kind of very complex pattern that may be spread over time with multiple reports and dozens of dimensions. Not something that you can summarize by looking at the average of a packet loss over the past few minutes, obviously. So we look at the interpretability, this kind of sequence of aggregated report using Shapley values and other kind of technologies. We even started to look at attention deep neural networks architecture. And this is very well known now because, of course, of the emergence of generative AI. You probably heard of this kind of architecture, attention. And I'm sure you heard of the attention is all you need white paper that drove the architecture of transformers. But in this case, we use a similar model using attention in DNN to really understand the dynamics of it. Again, you will find many more details in the white paper about these mechanisms and how they correlate. We look at the co-evolution of the attention scores and the KPIs, and we did find some very interesting outcome. And again, that shows you how subtle this kind of QE can be, and this kind of pattern has to be learned with QE model. There's no way you can come up with a set of rules where you would have a look at just the loss and the delay or the jitter and find some hard-coded values and just say, okay, the SLA is met or it's not met. This is way more complex than that. And this is where we need that. So now you may argue and say, well, okay, this is great, but you have done that for WebEx. What does that mean for other applications? So to that end, this is something we addressed, and we use something called multi-application model. And we wanted to see if you could use a model that was trained for a given application, such as voice and video with WebEx, and you can basically use it for other video conferencing applications such as Zoom, Microsoft Teams, or even, HAR, for example, which is mostly for web-based applications. So maybe I should, at some point, spend more time with you and explain how you can use different kind of technologies in machine learning so that you can do this sort of things. It has been a challenge, I would say, with machine learning to train for a given task and then try to propagate and use, if you will, the same model for a different tasks. Usually when you train for the second task, you tend to forget the first one. It's known as catastrophic forgetting, but there are many mechanisms to do that, such as transfer learning, domain adaptation, and we've used somehow these kind of technologies to do that. We use both a real bot, but of course also mTurk from AWS, where you could basically come up with a set of a data set basically that you would show to user, and then that could be used, if you will, to come up with multi-application model, and the results are extremely promising. So I won't spend too much time on transfer learning, multitask learning, which is another way of doing that. We use also a technique called joint learning across multiple applications, but the bottom line is that even though the features may be slightly different, there are ways to adapt the input features so that you can train a model on a given application and use the same model for other applications, as long as they are basically related to the same task, which in this case was voice and video. So now you may say, okay, but what can I do with that? So I understand now what is the QE for my network. It has been learned dynamically, but you mentioned that, with cognitive, we could start tuning the network, make it self-healing network, and trigger some action in the network so that we optimize for QE. How can we do that? In fact, there are many things. In fact, there are many actions that people can provide. So here, I'm just giving you some examples. So suppose that you have a WebEx client where you have a speaker, you see that on the left, and then you've got a bunch of listeners. So what can happen is indeed a local WAN congestion. So in this case, suppose that you have a congestion on the WAN on the side of a speaker, and you may say, what could we do in order to optimize the experience of the listener? There are many things you can do. One of them is simply to play with QoS. So what do people do today? When they use QoS, they usually apply some static template and they just hope for the best. And of course, you can monitor, you can tune, but it's not an easy process. In this case, what I'm doing is just to say to cognitive networks, you can now play with QoS on that side if you detect a local WAN congestion so that you do improve the QE of a listener. That's just one example. Let me show you another one, an uplink degradation. So in this case, what can happen is that you are having exactly the same kind of issues, but there might be a middle mile congestion impacting the speaker. In this case, what can you do? Well, there are many things you can do. You can start rerouting the traffic using another backbone. So instead of using your ISP and then rely on BGP end-to-end, you may steer traffic and send it to Microsoft Azure, Google GCP, or other kind of hyperscaler backbone as well, right? You've got the choice between, again, Microsoft Azure, as I said, Google, AWS as well. And that may be an action that can be triggered by cognitive networks to basically improve the QE. Once again, remember now, you have a model that tells you the QE for your user is just one of the tools that can be used to improve the QE as a sort of a remediation action. There might be a third one, and this is just for the sake of illustration, which is a downlink degradation. And in this case, if you have such an issue, you can also build an alternate middle mile path via a CSP or SDCI provider as well. Yet another example that can happen. Okay, so I just wanted to show you that. Again, I could spend a lot of time on results, but the results have been extremely promising. We did accumulate an enormous amount of telemetry at high frequency. Again, look at the white paper on MIF if you are interested. We did accumulate a ton of information, raw data about this kind of telemetry. As you can see, in this case, we had more than 51 terabytes of data, which is enormous. We ran all this data to train multiple machine learning models where we could really assess the efficacy. And in short, I can tell you that this experiment has shown that it was possible to learn the QE using this kind of cross-layer approach. Of course, we did come up with a lot of performance evaluation metrics of the models. We looked at interpretability of the QE model to really make sure that these models did learn some interesting properties of the QE. So what I would like to say in conclusion, and we've been really, so what would I like to say in terms of conclusion? When you think about it, we came up with this notion of predictive networks. If you are interested, you can have a look. I have a lot of videos about that. And the idea was, instead of being reactive, we want to be reactive, but also predictive, something that we never did in the internet. In the case of cognitive networks, the idea was, when you look at QE, which is a very complex and sometimes subjective issue, the only thing we've been doing for so long was to say, that the delay, the packet loss, and the jitter should not exceed some static threshold. But of course, we've known for years that the issue was way more complex. It's just that we did not have a tool at the time to really model what was the source, what was driving QE for the user. So what we decided to do was to collect a fairly high number of labels and feedback from the user and couple these kind of labels with rich set of data from telemetry across the layers and see if we can train an algorithm to really understand the QE and model the QE. And the answer is yes, we managed to do that. Now, if you now have a QE model that tells you about the satisfaction of your user, you can start using model interpretability and identify the actual use case, the actual. Now, if you have a model that can be used to predict the QE of the user, you can use some tools related to model interpretability so that you can identify strong candidates for root causing. And because of that, you can then trigger some action to solve the problem. So you may say, well, okay, but is such an approach applicable to all applications? And the short answer is you may not have the luxury to have so many labels for all of the applications in the networks, but if you can, you may now, okay. So what conclusions? So let me go now to the conclusion, and I think this is very important to step back for a minute. When you look at predictive networks, which was a new concept we came up with in 2019, we were looking at it and say, for the past 30 years, we have been using reactive mechanism. So you wait until you have the issue, and then you react and you try to fix it. Is that a way to use machine learning so that we can model the network and the internet and predict some issues before they happen? In the case of cognitive networks, the idea was, if you look at the past 30 years, the way we've been approaching QE was to say, we'll be looking at loss, delay, and jitter, define some hard-coded values that should not be exceeded at the risk of violating the SLA. And we knew that it was a very, very naive approach to the model of QE, but we did not have a tool to decipher what QE was about. And that was time to revisit that assumption and start using machine learning to do that. So what we've done in this experiment was to train multiple machine learning models, gather a very rich set of user feedback in a very simple form of quality is okay or it's not okay, then train these models and see if indeed we could predict what was the QE. And because you have a model now that has proven to be very efficient, we can use interpretability of the model and find some candidates for root causing. So you may now say, well, yes, but is it possible to apply the same approach for all of the applications in the world when there are thousands of applications for which we don't have a luxury to gather hundreds of thousands of feedback? And of course, it's not always possible to do that, but with mechanisms such as transfer learning, multitask training, we've shown that very likely a single model could be used for multiple applications that are basically in the same class of applications, such as video conferencing. And you may not need to have a model predicting the QE for all of the applications in the world. But for the critical ones, that might be really worth it. So what could drive the next step in this case is to use different kind of mechanism to tune the network, to adapt the network so that in this case, you can understand the QE, you can find what is going to improve the QE, and you can trigger some action in the network. You may want to tune QS on the fly, you may want to redirect according to the predicted QE along alternate paths using different kind of gateways, different kind of network, such as the hyperscaler network. So I did find this experiment extremely promising because that would be a paradigm shift from the very naive approach we've been using in the internet for 30 years to something where we see one more time, if needed, that MLAI could bring us to the next generation of networks, where now we do understand the QE, but that's not it. We can also tune the network, not for the delay of the bandwidth of the link usage or you name it, but for QE and for maximizing the user experience for the network. So with that, thank you for your attention. And I think that, again, that could be one of these innovations for the future of networking.